Good morning, students. Our today's topic is finite dimensional norm spaces and subspaces. So the first lemma is linear combinations, which states that if we have a linearly independent set of vectors in a normed space X, where X has any dimension, and the set which is linearly independent is denoted by the vectors x1, x2, x3 up to xn. Then we are to prove that there is a number C which is positive such that for every choice of the scalars alpha 1, alpha 2, alpha 3 up to alpha n, we have the norm of this linear combination formed by the vectors x1, x2, x3 up to xn. Means this linear combination is alpha x1 plus alpha x2 plus alpha x3 and so on alpha n xn. Norm of this linear combination is greater than or equal to C times the sum of alpha 1 mod plus alpha 2 mod and so on alpha n mod. This lemma is called linear combinations lemma, and we will use this lemma later in the theorems. Now to prove it, let us denote alpha 1 mod plus alpha 2 mod and so on up to alpha n mod by the number s. Now if s is 0, in that case alpha 1 mod plus alpha 2 mod plus so on alpha n mod, that will be 0. Now because this expression is a sum of non-negative quantities, so if their sum is 0, each quantity will individually be 0. So each alpha j will be 0. So the inequality 1 holds for any c in this case. Now let us take the second case when s is positive. Now in this case we can write this inequality into another form. In the right hand side, if we substitute the value of this expression which we have taken as s, dividing through by s in this equation, we get 1 by s into the norm of alpha 1 x1 plus alpha 2 x2 and so on alpha n xn. This is greater than equal to c. Now we can take the scalar 1 by s inside the norm. So this will become norm of alpha 1 by s into x1 plus alpha 2 by s into x2 and so on alpha n by s into xn. Now this norm is greater than or equal to c. Now let us take the notation beta I is equal to alpha I upon s. So this will become beta 1 x1 plus beta 2 x2 and so on beta n xn norm greater than or equal to c. Now if you find the sum of the numerical values of beta i's, this will become summation alpha 1 by s mod plus alpha 2 by s mod and so on alpha n by s mod. If you find this sum, we can see that summation mod of alpha I, that we have denoted by s. So this will become s divided by s. So this will be 1. It means the sum of the numerical values of beta i's, that is 1. It means in equation 1 is reduced to the another form which is given by beta 1 x1 plus beta 2 x2 and so on beta n xn norm is greater than equal to c. So we are to prove this inequality now. So in order to prove this inequality, it is sufficient to prove that there exists a positive real number c such that the equation second holds with this condition that the sum of the numerical values of beta i's is 1. We will prove it by contradiction method. Let us suppose this result is false. Then there exists a sequence ym of the vectors of the form. These ym will be of the form of linear combinations beta 1m x1 plus beta 2m x2 and so on beta nm xn, where the sum of the numerical values of these scalars, that will be 1, such that ym norm approaches to 0 as m approaches to infinity. Now we reason for this as follows. Because this sum of numerical values of beta i's m, that is 1, and this is true for every m, and each term in the sum that is non-negative. So we can say that mod of beta I m, that is less than or equal to 1 for every m, and hence for each fixed I, the sequence beta I m, that is a bounded sequence. If we take I is equal to 1, then the sequence beta 1 m, beta 1 1, beta 1 2, and so on, this sequence is a bounded sequence. So we can use Bolzano-Weierstrass theorem. According to this theorem, every infinite bounded sequence has a cluster point. So this bounded sequence will have a cluster point, and hence we can say that this sequence has a convergent subsequence. So let us take beta 1 be the limit of that sequence, and let us take the corresponding subsequence of the sequence ym be denoted by the sequence y1m. By using the same arguments, the sequence y1m will also have a subsequence, and that subsequence we have denoted by y2m, and for which the corresponding subsequence of the scalars beta 2m, that converges. Now because this converges, so let us take beta 2 be the limit of that converging subsequence. We can continue like this. After n steps, we get a subsequence ynm of the sequence ym, where the terms are of the form of the linear combinations, having the form gamma 1m x1 plus gamma 2m x2, and so on, gamma nm xn, where the sum of the numerical values of these gamma im, that is 1, and gamma im converges to beta I as m approaches to infinity. Now let us take y with a linear combination denoted by beta 1 x1 plus beta 2 x2, and so on, beta n xn. Now let us find the sum of numerical values of beta I. Substituting the value of beta I. Now what is beta I? Beta I is the limit of the sequence gamma im. Substituting the value, and this can further be written as summation beta I mod is equal to limit m approaches to infinity, the sum of numerical values of gamma im. Now because this is 1, so the sum of mod of beta i's, that is 1. Now because this sum is 1, so we can say that all the beta i's are not equal to 0. Now because we are given that the set consisting of the vectors x1, x2, x3 up to xn, that is linearly independent set, and also not all the beta i's are 0. If a set is linearly independent, then the linear combination is equal to 0 implies all the scalars are 0. But here, because all the scalars are not 0, therefore we can say that this vector y, that is not equal to 0. Also we have taken the sequence gamma im converges to beta I for every I, and now we will prove that ynm minus y norm approaches to 0 as nmm approaches to infinity. So now let us consider the norm of ynm minus y, substituting the values of ynm and y here, and now we can take xi common from these two terms. This can be written as the norm of summation gamma im minus beta I into xi. Now by using the triangle inequality norms, this expression is further less than or equal to summation norm of gamma im minus beta I into xi. Now we can use absolute homogeneous property of norms. This is scalar and this is vector. So norm of alpha x, that is given by alpha mod into norm x. So using this property here, norm of ynm minus y is less than or equal to summation mod of gamma im minus beta I into xi norm. Now because gamma im converges to beta I, so this will converge to 0. So ynm minus y norm approaches to 0 as m approaches to infinity. So this proves that the sequence ynm converges to y. But we already have taken the sequence ym converges to 0, and because this is the subsequence or sequence ym, and therefore the sequence ynm converges to 0, and because the limit of a sequence is always unique, so it means y should be 0. But this is a contradiction to the fact which you already proved, that y is not equal to 0. So it means our assumption is false. So we can say that there exists a number c which is positive number such that the norm of alpha 1 x1 plus alpha 2 x2 and so on alpha n xn, this norm is greater than or equal to c times alpha 1 mod plus alpha 2 mod and so on alpha n mod, and this completes the lemma which is called linear combinations lemma. So we will use this lemma in the next theorem, and we'll do the theorem tomorrow.